Now what is an orientation? A normal vector field is defined by N of P equal to plus or minus gradient of f of P divided by the norm. Now if you have a surface with this choice of normal vector field, then the surface is called an oriented end surface. So these are basic definitions. Now what is a Gaussian curvature? There is a map, Weingarten map, which goes from SP to SP. Now what is SP? SP is the tangent space at the point P, which is defined by LP of V is negative gradient of V of N, where N is the normal. Now the Gauss-Kronecker curvature is defined to be the product of all the eigenvalues of this LP, where this eigenvalues are also called principal curvatures of S at P. So basically what a Gaussian curvature is how much a surface bends at the point P, or how much it curves at the point P on the surface. That's what it means. Now what is the volume form? So volume form on S at P is a function zeta, which assigns to each ordered set of n vectors in SP this number right here, where N of P is the normal to the surface. So that's the volume form. Now before we know the definition of geodesic curvature, we need to know the definition of the covariant derivative. Okay, so now what is a covariant derivative? So let S be an n surface, and alpha be a parameterized curve in S, and X be a smooth vector field tangent to S along alpha. Then the covariant derivative of X is defined to be this thing. Now what does this thing mean? So we'll look at a figure. So this is the tangent space, and this n is the normal, and if x dot is pointing that way, then the orthogonal projection of x dot onto the tangent space is x prime. Okay, that's what x prime means. Now there's another notation. For v belonging to SP, we will denote JV to be the vector obtained from V by a positive rotation in SP through IO2. So now what does that mean? So now I have a figure. So if this is your surface S, this is the tangent space at P, this N is the normal. If this V is a vector in the tangent space, then if you rotate it by 90 degrees, you get the JV. Does that look right? So that's JV. Now, the geodesic curvature is defined to be, so if alpha is any unit speed curve in U is an open set in S, the geodesic curvature is defined to be the covariant derivative of alpha dot dotted with J alpha dot. So it's the orthogonal projection of alpha double dot onto the tangent space dotted with J alpha dot. Now this geodesic curvature measures how much alpha deviates from being a geodesic. And we note that this alpha is a geodesic if and only if this k of g is equal to 0. Okay, now what are exterior angles? The exterior angles of a regular triangle phi. For regular triangle phi, I mean it's a map from R2 to the surface, which maps the triangle. Okay, now the exterior angles are unique real numbers theta I, such that Vi can be written like this. I'll show you what that is. Where Ui is this thing, Vi is that thing. Now what does all this mean? So if you have a map from a triangle, so this is in the surface, this is in R2. So now what is the exterior angle? So U1 is a tangent vector at the end point of alpha 1, and V1 is a tangent vector at the starting point of alpha 2. Okay, and the angle between them is the first exterior angle. Similarly, U2 is the tangent vector at the end of alpha 2, and V2 is the tangent vector at the starting of alpha 3. And the angle between them is theta 2. Okay, that's how we'll find the exterior angles. Now, what is the Euler characteristic? Now, given a triangulation tau, it means if we divide the surface into triangles, so, and there are f number of faces of the triangle, e are the number of edges, and v the number of vertices, then the Euler characteristic chi can be given as f minus e plus v. Okay, this is the Euler characteristic. Okay, now we'll look at some basic examples to see how this thing works. So consider a Euclidean triangle and apply the Gauss boundary to it. Okay, now we know that the curvature of a plane is 0. So this thing drops out. Okay, now the edges or the boundary of the triangle are geodesics because they are straight lines. So this thing drops out too. And then we get that the sum of exterior angles of a triangle is 2 pi. Now why is this chi equal to 1? So chi by definition is v minus e plus f. So the number of vertices here are 3 minus 3, the edges, and 1 face. So chi is equal to 1. So basic example shows that sum of the exterior angles is 2 pi. Now next example, we consider a disk. Okay, now in the form of disk, again this thing goes away because we're on the plane. Now what is the sum of the exterior angles? So if you consider a disk, what is the exterior angle here? It is this vector and then again this vector. So the theta i's are always equal to 0. Okay, so the sum of the theta I also disappears. And similarly we get that the total geodesic curvature of this thing is equal to 2 pi. Now what does that mean? This curve totally deviates from being a straight line by 2 pi. That's what that means. Okay. And we'll consider example 3, which is a hemisphere. Now how does this thing drop out? What is the boundary of a hemisphere? It's the equator, which is clearly a geodesic. So this term drops out, plus what is the sum of the exterior angles? So if you consider a hemisphere, again, the exterior angles is this point right here, which is 0. So similarly, this term drops out. And why is chi equal to 1? So now how can we triangulate the hemisphere? So you take a vertex here, and suppose there are p vertices on the boundary. Okay, you join every vertex to triangulate the hemisphere. Then clearly there are how many vertices? The number of vertices is p plus 1. If there are p vertices on the boundary, minus how many edges? There are p edges on the equator and p of the new edges. So this is 2p. Okay? And how many faces? So the number of faces is equal to the number of these edges. So that is plus p, which is clearly equal to 1. So we get chi is equal to 1. So we get, and we know that k is equal to 1 in case of the hemisphere, because the curvature of a hemisphere is 1. So we get that the area of the hemisphere is equal to 2 pi. That's because you integrate the volume form to get the area of a 2 surface. That's the thing. Okay, now we'll try to see the local form of the Gauss bonnet and try to extend it to the global form. So now what does the local form say? Let S be an oriented 2 surface in R3 and phi be a regular triangle in S, like the one we defined before. Then the integral of Gaussian curvature plus the integral of the geodesic curvature is equal to 2 pi times the exterior angles. So this is the local form of this thing, and beta from A to B is a unit speed parameterization of the boundary, and everything else is the same. Now we'll see how we can prove this thing. So now before that we need to know the concept of the angle of rotation. So now let alpha be a parameterized curve in S, and y and z be smooth unit vector fields tangent to S along alpha. Then the vector z of t can be written as cos theta of yt plus sin theta jt, where this theta is the angle of rotation from y to z. Now I'll show you the figure on what does that mean. And theta b minus theta a is the total angle of rotation. So what does that mean? So if you have a vector yt at a point alpha t, then you rotate y of t by 90 degrees, you get jyt, and z of t is right here. So the angle between z of t and y of t is the angle of rotation. Okay? And if this angle is theta a and this angle theta b, then theta b minus theta a will give you the total angle of rotation. Okay? Now we need to define what is a connection form. So let S be an oriented two-surface or a two-surface with boundary. X be a smooth unit tangent vector field on U. We define the smooth one form omega to be dv of x dot j of xb. Now what is this dv of x? This dv of x is the orthogonal projection of gradient of v of x on the tangent space. So the earlier it was x dot on the tangent space. This dv of x is the orthogonal projection of this on the tangent space. Okay, now what is the geometric meaning of this? So we shall use lemma 1. So if s, x, u and omega are things as before, so let alpha be a smooth unit curve in U. So now what does this lemma say? So if alpha is a smooth unit curve in U, so if this is alpha, then the total angle of rotation alpha dot with respect to the vector field x is equal to this integral right here. So if this is alpha dot, okay, and this is x, the vector field x, then the integral a to b kg minus the integral over alpha of omega is equal to, okay, this angle is theta 0, and this angle right here is, say, theta t, where this is x and this is again alpha dot, and this is given by alpha t minus theta 0. That's what the integral gives you. Okay. Now, lemma 2, so let s, u, x and omega be as before. Then the exterior derivative of omega, denoted by d omega, is equal to the negative of the curvature times the volume form. Okay, these are the proofs that we'll use to prove the theorem. Now, we shall also use the Stokes theorem, which says let S be an end surface or an end surface with boundary. So let omega be any smooth one form, and let phi be either be a singular disk, a singular half disk, or a singular triangle in S. So any of this one things on the surface, then the integral of d omega over the surface is equal to the integral of omega over the boundary of the surface.
Actually, the end surface has to be two surfaces.
Right, and in our case, n is equal to 2. So we're only dealing with two surfaces. So over there, n means the two surfaces. Okay. Now let's try to see the idea of the proof of the local form. So now by lemma 2 and the local version of Stokes theorem, we get that this integral is equal to this integral by the second lemma 2 and Stokes theorem. Now this is equal to this by the Stokes theorem. This is equal to this because beta is the parameterization of the boundary. And this is equal to this, where beta 1, beta 2, beta 3 are the three edges of the triangle. Okay. Now, well, lemma 1, we know that this minus this is the total angle of rotation of alpha dot with respect to x. And we shall denote it by, so it's the same as this one, P1. So in this case, your alpha dot is equal to beta 1. Okay, so we get this thing. Now, we shall choose an angle theta 0 so that b1 dot of a1, so in this case, this vector can be written as cos theta naught of x of beta of a1 plus sine theta naught jx of beta of a1. Now, what does that mean again? So if you have a triangle on the surface, if this is the vector beta 1 dot of a1 and this is x of b1 of a1, then you rotate this by 90 degrees and then you can write this one in terms of this and this. That's what the earlier statement meant. Okay. And similarly, beta 1 of b1 can be written as cos theta 0 of p1 plus bx of beta of a2 plus sine theta 0 plus p1 jx of beta of a2. Now, why is that the case? So let's see. So now this vector beta 1 dot of b1 can be written as this angle. So this times cosine theta of this angle plus you rotate this by 90 degrees and sine theta naught plus p1 of that angle. Now, why is this angle theta 0 plus p1? So it follows from this thing. So if that angle is theta 1, theta t, then theta t can be clearly be written as p1 plus theta naught. So that's how you get this angle from. It's a little confusing, but this is where we get this angle from. And similarly, we define theta 1 to be the exterior angle between these two. And then this vector can be written as this times cosine theta of this angle plus sine of this angle jx of beta of a2. So beta 2 dot of a2 can be written as cosine of the new angle x beta of a2 plus sine this angle jx beta of a2. And then similarly you go from point to point. So similarly you go from point to point. You do it at this point, this point, this point, and come back to the original point. Okay, when you come back to the original point, you get beta 1 dot of a1 is equal to this thing right here. Okay, and when you compare the two forms of beta 1 dot of a1, you get that the summation is equal to 2 pi times an integer. Okay, where k is an integer. And then we plug everything into the thing we started with. So we get this. And now in place of summation of few i's, we substitute this. So we get that. And so we get 1 over 2 pi times this is equal to k for some integer k. Now by an argument of continuity, we can show that this k is equal to 1. And then we get our required result. We can also show this k is equal to 1 by b minus e plus f. Also in that case, this k is equal to 1. Okay, so we get the result of the local form. Now by using this, we shall try to prove the global form. So let's look at the global form again. So S be a compact oriented two surface with boundary, then the total geodesic curvature, the total Gaussian curvature plus geodesic curvature for summation of theta is equal to 2 pi chi of S. Now, so if you are given a triangulation tau of the surface, we apply the local Gauss bonnet to every theorem, every triangle, and then add the results. Okay? So this is what we get. Now, where f is the number of faces of the triangles, of the triangulation. Okay, now we consider the interior angle of the triangle. So we take the sum of all the interior angle of the triangle. We get the external angles is equal to 3 pi f times the interior angles, where this delta I is the interior angles of each triangle. Okay, now we shall use some notation to see how we can prove this. Now, suppose this is your surface, just an example, and this is the triangulation of the surface. By EE, we will mean the external edges of the surface. By EI, we will mean the number of internal edges of the surface. Okay. By VE, we shall mean the number of external vertices. Okay, now we will see what that is. By VI, we will mean the internal vertex. That is, the vertex which is not on the boundary. Okay, by VEC, we will mean the number of vertices of the boundary. So the number of vertices which are the vertex of the boundary. And by VET, we will mean the new vertex that are formed due to triangulation. Okay, now clearly, the number of external vertices is equal to VEC plus VET. Okay?
So what was the difference between external vertices and boundary vertices?
What is the difference between external? So when we do the triangulation, we get new vertices, right? And VET are the actual vertices of the boundary.
Okay.
And VET is the new vertices that are formed due to triangulation, which were not originally the vertex of the boundary. Right, and then clearly this total number of external vertices is equal to these new vertices plus the original. And then since this is a closed boundary, the number of external vertices is always equal to the number of external edges. That is always the case. So now after knowing all this, we can show that the sum of the exterior angles is equal to 2 pi times EI, 2 pi times the external edges, minus 2 pi times VI, which is the internal vertices, minus pi of VE, which is the external vertices, minus pi of the new vertices formed, minus the pi of VEC, the original vertices, plus the summation of theta L's. Now theta L's are the theta L's are the actual theta L's are the external angles with respect to the boundary. So those are theta L's. Okay, then by combining the terms, we get that 2 pi E plus 2 pi V plus this is equal to this. Now, we all see how do you combine terms? So we take pi common here. VET plus VEC will give you VE. So pi VE minus pi VE will give you 2 pi VE. Then you factor out 2 pi. You get VI plus VE, which is clearly V. Okay, now put this into the original form we started with, into the sum. We get this plus these are the exterior angles now, which is equal to 2 pi V minus E plus F, which is clearly equal to 2 pi chi. And hence we get the result for the global form. Okay, now we'll try to look at some application. Do you all have any questions on the previous slides or anything? Okay, now we'll try to look at the application of the Gauss bonnet. Now, any simple closed curve with total geodesic curvature 0 on a sphere will bisect the area of the sphere. So now what does that mean? If you have a curve on the sphere such that the total geodesic curvature of the curve is 0. This curve may not be a geodesic, but the total curvature has to be 0. Then this curve will bisect the area of the sphere. So the area of S1 has to be the area of S1 has to be the area of S2. Now, how do you do that? So you apply Gauss bonnet to each of them. So we apply Gauss bonnet to each of them. Well, these are the exterior angles with respect to this boundary, and these are the exterior angles with respect to this boundary. And then we subtract the two. So we subtract the two, we get this minus this, and so we subtract the 2. Now, how does this term drop out? So let's try to see that. So if you have a sphere, and if you have a curve, so this is S1, this is S2. Now, the orientation with respect to S1 goes this way. Okay? And the orientation with respect to S2 goes this way. So we see that the total geodesic curvature with respect to boundary of S1 is equal to negative of the total geodesic of boundary of S2. Because the orientations are opposite. Okay, and then we try to plug this thing in here. We get 2 times the total geodesic of S1 kg, which by assumption is equal to 0. Okay, so this term drops out. Now, why do the angle terms drop out? So if you have a vertex here, what is the exterior angle with respect to this vertex? So you go this way, and then there's another vertex here. So this is one of the theta, let's call this theta 1. Okay, this is the exterior angle with respect to S1, and the exterior angle with respect to S2 coming that way will be this line extended here, and this line over here. So that's the exterior angle with respect to S2. We'll call it theta 1 dot. Now, since they live in a tangent space, theta 1 dot will be clearly equal to theta 1. Similarly, that's the case for every exterior angle. So the sum, so the subtraction drops out. Okay? Now, why is chi of S1 equal to chi of S2? So if you take a vertex here and join all the edges, join all the vertices on the boundary. Okay, similarly take a vertex here and join the same vertex to these guys. We get a similar triangulation of both the S1 and S2. So by this one we get chi of S1 is equal to chi of S2. So by doing this, this term also drops out. Okay, and so we get chi of, so the area of S1 is equal to the area of S2. So that's how it bisects the area of the two S1 and S2. Okay. Now we'll try to look at application 2. So if S is an orientable surface of negative or 0 curvature, then two geodesics C1 and C2 will start from a point P, cannot meet again at a point Q, in such a way that the traces C1 and C2 constitute the boundary of a simple region R of S. So by simple region we mean it's homomorphic to the disk. Okay, now you look at the figure of this thing. So this is C1, okay, and this is C2. Now suppose they meet at a point Q such that this is a simple region R, and C1 and C2 are geodesics. So by applying the Gauss bonnet, we get that the integral of the curvature over the region R. Now clearly the geodesic curvature drops out because these two guys are geodesics. That thing drops out. Plus θ1 plus θ2 has to be 2 pi. Pi is equal to 1 because it's a simple region. Okay. Now let's see, why is this a contradiction? So if this is negative, then θ1 plus θ2 has to be greater than 2 pi, which is clearly not possible by the definition of exterior angles. Okay, and if this term is equal to 0, then θ1 and θ2 both have to be pi, which is also not possible because they simultaneously cannot be equal to pi. So in that case, this is a contradiction. So this thing cannot happen. So a geodesic starting from a point P cannot meet at a point Q such that they enclose a simple region. So that's application 2. Now we'll try to see application 3. So let S be a cylinder with negative Gaussian curvature. So the total curvature in this case is negative. Then this surface S can have at most one closed geodesic. So that is application 3. Now I haven't written anything for this, so I'll write it on the board. So now how do we try to prove this? So let C1 be the first closed geodesic, okay? And we know that the cylinder with negative curvature is homeomorphic to a plane with one point removed. Okay, so psi from S to a plane without a point is a homeomorphism.
This is a topological thing. It has nothing to do with the curvature.
Right. So this is true from topology, nothing to do with the curvature. Now we assume that let C2, now clearly psi of C1 will look like this on the plane. Now we assume that C2 be another closed geodesic. C2 be another closed geodesic. Now, then psi of C2 shall look like this. Now, why will psi? Now we will try to prove that C1 intersected with C2 has to be empty. So this is we try to prove. Now, why is this true? So this is the claim. Now, why is this true? Because if they intersect, so suppose they intersect, then psi of C1 intersected will, psi of C2 will be non-empty if they intersect. Okay, in that case, if this is psi of C2, then this region over here will enclose a simple region, which is a contradiction by application 2. Because these two guys will clearly be geodesics. That's a contradiction. So they can never intersect. So this is how they should look like. Now, we apply the Gauss-Bonnet theorem to the interior of R. Now, what is R? R is the region between, so R is this region. The region enclosed between the two geodesics.
So apparently the plane P is inside the
P is a
images.
point, right. P is a
Correct. Why can't it be outside the curves?
why can point P be outside the curve? Because so if the point P is outside both the curves.
Well, it could be outside one and inside the other. I mean, I think it's important in the other end that this is exactly the situation, but why can't other possibilities occur?
I'm not pretty sure about that.
Why can't you have a C1 that's like crawling on the side of the cylinder rather than moving around it?
Well, even
Yeah, that's exactly the question.
right. Well, even in that case, we take the homomorphic image of it. Okay, but now the question is, why can P be outside? So if P is outside, I'm not sure what will happen. Right, so let's try to prove it in this case then. So we take the inverse image of the region between them, and clearly the total geodesic curvature vanishes because these guys are geodesics. So the geodesic curvature will vanish, and now the exterior angles of P inverse of R, so clearly these guys are the boundary, and the exterior angles will clearly be at this point, which is again 0. So the exterior angles will cancel out. So there are no exterior angles either, which will be equal to 2 pi chi r. Now, since this is a homeomorphism, we take the chi of r, so inside the plane, and which is a simple region, or which is an annulus. So this is homeomorphic to annulus. So we try to calculate the chi of the annulus. So the chi of the annulus, so this is the triangulation of the annulus. The number of vertices are 4 minus the number of edges, 2, 3, 4, 5, 6, and clearly the number of faces is 2.
Well, it's not a triangulation because some of the faces are quadrilateral, but it's okay because it's topological algorithms.
Right. We can even consider like a triangle inside a triangle, and then try to triangulate this thing and prove. So this is completely equal to 0. So we get that the right hand side is equal to 0. Now which is a contradiction because this thing has to be negative. Since this thing has to be negative, it cannot be equal to 0.
It's much the same argument why P cannot be left outside the images, because they contradict again Gauss-Bonnet. If P were outside, apply Gauss-Bonnet inside, for instance, the image of, well, C1, correct?
Right.
So then the curvature would be negative, the total Gaussian curvature
Right.
would be negative, but there are no angles, the boundary is geodesic, no geodesic curvature, and being a simple agent, the polar characteristic
Right.
would be being
Right.
1, so positive equals negative.
Right. Right, okay. So that's it with the presentation. I'd like to thank Dr. Randall, Dr. Raya, the math department, and all here.
Great. Questions?
Well, I know I went a little fast because it was too
Yeah.
much to cover.
So I have a question, a little bit of history. Do you know what Gauss's contribution is versus Bonnet's contribution?
Well, I read a paper on this in which it showed that somebody else proved this theorem. And then these guys somehow got their hands on this thing and got their names. It was that paper we talked about, all the way with Gauss-Bonnet. Tushar and me read it together. Tushar. But I'm not sure in this case what is the history.
Well, Gauss is credited with a version where the boundary is geodesics, like straight
Right.
segments and Euclidean triangles or geodesics on surfaces. And Bonnet extended it to boundaries which are not geodesics.
Right. Okay, so the version without the boundary is the Gaussian.
No, no.
Oh, the version
without
with the boundary,
geodesic
the boundary
boundaries.
is the geodesics.
Yeah.
Okay, okay.
Both have boundaries, however,
Right, right.
the distinction is being geodesics versus
Right,
not.
right. I guess that was it.
Very good. So if you step out, log everybody else except Dr. Sohil, we have